All right, so today we have Markus Dierigl tell us about to be explored, Bordisms, duality, and the Swampland. Take it away.
Thank you very much. So first of all, thanks a lot for the invitation. I'm excited to talk about this recent work of mine. So I'll mainly focus on these two works here. So one appeared this week and the other appeared end of last year. And it's together, work together with Aaron DeBray, who is a mathematician at Purdue University, Jonathan Heckman at UPenn, and Miguel Montero, who is just transitioning from Harvard to Madrid, essentially. And in the second paper that appeared a little bit earlier is together with Jonathan, Miguel, and Ethan Torres, who is one of Jonathan's PhD students. However, I also want to point at a couple of earlier works that are related, and I will come to what the relations are during the talk. And with that, I also want to encourage you to interrupt me essentially at any time. So I hope I give a sufficient introduction to the topic and sort of the assumptions that go into our investigation. But if you're unhappy with something or want some more details on certain aspects, please feel free to just unmute yourself and ask. Okay, so I'll start with one of the Folk's theorems that have been around for quite a long time already, namely that in quantum gravity, we don't want global symmetries to be present. So the standard arguments why this should be the case is, well, some entropy arguments related to black holes. So you can essentially build an arbitrary number of small black holes if you have some continuous global symmetry in the system. And there have been some maybe a little bit more precise motivated statements in the context of holography by Harlow and Oguri 5 years ago, where you can associate the action on bulk operators and the presence of global symmetries that are not consistent with this holography picture. So then if we're faced with a problem that we want to study our favorite toy model for quantum gravity, and we find global symmetries, there are two options to get rid of them. Either we break them or we gauge them. Once they're gauged, they're also fine. And so what is actually the problem with global symmetries is, well, whenever we have this global symmetry in the system, there is a charge, let's call it Q, that is conserved. And moreover, and that is the distinction to the gauge charges, it doesn't cost any energy. So there is no field that is associated to that charge that tells you that once you switch it on, there is some energy budget that you have to satisfy. Okay. And in principle, this charge then can be used to label different sectors of the theory. That's saying that a global symmetry specifies the states or separates the states in a Hilbert space into different sectors labeled by the charges. And conserved essentially means it's preserved under various different deformations. So one, of course, is time evolution. That's more the traditional way of what conserved means. So if you measure a charge at time t and some later time, they should coincide. But in general, global symmetries should also be preserved under more abstract deformations of space-time and other things. So, however, if there is a conserved charge here, that tells you that there is the sectors and you cannot connect to the trivial sector, right? So whenever you try to deform your theory, there is this charge that you need to preserve because of the global symmetry. And especially if you think about a boundary of a space-time, right? This can be thought of a connecting sector Q with nothing, and nothing clearly sits in the trivial sector. So there is no way to support this global charge Q in nothing. So therefore, global symmetries can be viewed as basically an obstruction to defining a boundary conditions for your theory. It's an obstruction to deforming a sector with charge Q into the trivial sector. Okay. And this leads me to a maybe slightly different definition of this no global symmetry conjecture, which has been phrased a couple of years ago by Jake McNamara and Qumrun Waffa, and it's called the Cobordism Conjecture. So let's say we demand that every quantum gravity theory should allow for a boundary condition, right? So this means that every quantum gravity theory should be possible to be connected to the trivial sector deformable to nothing. If this is the case, well, then we can get rid of the charge, right? Because the trivial sector has no charge. And that tells you that the charges are not preserved. So there cannot be any global charges. So in a sense, this no global symmetry conjecture in the Cobordism conjecture are heavily related. And here is more the stressing on I can always deform my theory to nothing in the sense that I can always find consistent boundary conditions to my theory. Now, how can I do that? Well, I just told you that if I have a global charge Q that is preserved, right, I cannot connect to the trivial sector. So I should include now objects that can be potentially looking a bit violent from the deep IR perspective. So they can correspond, for example, to singular gauge configurations that, however, have the effect that they change the global charge. And by doing so, the global charge is not anymore conserved. So you're really breaking the associated global symmetry. As an aside, there's also this gauging part. So in this talk, I'll mainly focus on breaking of global symmetries rather than gauging. Gauging would be another option. It is more like including tadpole conditions, saying my quantum gravity theory is only well-defined in backgrounds where the global charge has to vanish anyway. Right. So if you want an example in mind, so if you try to put the heterotic string on K3, that's not allowed, right? Because you have to put additionally some gauge bundle that takes into account this first Pontryagin class of the K3 manifold. So this would be heterotic on K3. It's not allowed, but you can basically compensate it by switching on additional gauge field configurations. This is sort of what gauging is supposed to be. But again, this is probably the last time I'll mention that, and now we'll focus on having objects that actually allow the transition of charges. Now, let me discuss a very simple example. Let's take a two-sphere with a U1 principal bundle that has a topologically conserved quantity, which is just the magnetic flux through this two-sphere. And there is no way to get rid of it with a nice U1 gauge configuration. So there is no way essentially of deforming the sphere to nothing. So what do we have to do? Well, now we have to include these objects that allow these deformations. And in this case, it's rather simple because they are given just by monopoles. In the pure U1 theory, these monopoles indeed are singular gauge configurations. So the gauge field is not well defined at the core. There's various solutions in the UV. You might complete it from U1 into some non-abelian group, and then you get the standard Topf-Polyakov monopole, for example, that are smooth configurations. But once we do that, these transitions suddenly are allowed. So for example, naturally, I can now deform the sphere to nothing when I just put a monopole inside that changes the magnetic flux accordingly. And this is just another picture that is more analog to what I drew before. Okay. Now, this deformation classes, so now the question is, can I deform this manifold with this structure into that manifold with the same structure? It has a nice mathematical context and is given in terms of Bordism theory. And this is precisely the content is, well, asking, deforming a manifold from this shape into that shape is possible whenever I can find a D+1 dimensional manifold that connects the two end as boundary, and that also preserves the structure that I impose. So that can include spin structure, orientation, can also have gauge fields, and so on and so forth, right? And then, of course, our question is, well, we want boundary conditions for all possible manifolds. So actually, we want all the Bordism classes to vanish. If that is the case, then I can take everything and deform it to nothing. So no global charges in the implication before. So let's test that in the example that we had before. So let's take the two-sphere. Let's say this is a two-dimensional spin manifold with a principal U1 bundle. The associated Bordism group is written like this. So this is the dimension of the manifold, omega 2. This is the structure associated to the tangent bundle or to geometry gravity sector, if you want. So we want the spin structure. And then this associates also maps into the classifying space. And that's the information that encodes the U1 bundle on top of that. This has a Z factor, which is precisely generated by those spheres, two spheres with a given magnetic flux through them. So indeed, we find that in this example, the Bordism class is non-trivial, so we couldn't deform it. And then we have to include a defect that would violate one of those structures. For example, it would lead to a, now, if we take the monopole again, it would lead to a singular gauge configuration. Okay. Now, in our setup, we want to do that in string theory, where this manifold we're talking about and want to deform to nothing arises as a compactification space. So our setup will be type 2b, supergravity, or type 2b string theory. And we want at least one non-compact directions, meaning that our manifold should be of dimension 9 or smaller. And then boundary conditions can essentially be associated to shrinking this space to nothing. This means that the Bordism classes of type 2b should all vanish. Then we are guaranteed to have no global charges in the setup. And that is the main topic. So the topic of this talk will be, well, is the Bordism group of type 2b in dimension k with k smaller or equal to 9 trivial? And if not, what kind of defects, what kind of objects do we have to include in order to allow for these deformations to nothing that then in turn can be interpreted as a break the associated global symmetries? Just one caveat here is that we're not discussing the full picture. This would be way more complicated than what I will tell you today. We're just discussing an approximation. So we just take a subset of the information that is needed to define type 2b supergravity. And this subset will be the space-time manifold. So especially the fermionic and bosonic natures of field, as well as the duality bundle. And we'll see that they're actually mixing. So those two notions are related in some sense. What we're not sensitive to, however, is, for example, additional background gauge fields that we know that we have in terms of the Rameau fields and their fluxes. So in the solutions or in the defects that I will discuss later, we always feel free to add the Rameau charges if needed in order to have a nice interpretation. And of course, this would be an extension of our work to really include them in the full Bordism discussion. So are there any questions around so this is the setup of today's talk, and I'll basically go through the approach that we took. Okay, so again, interrupt me at any time. So since this is quite a vast subject and you can get easily lost in all of these investigations, one of my very good friends, Paco, was nice enough to draw a map that sort of guided us through the work, and also is part of one of the papers, the big paper that I mentioned at the beginning. And there is different paths that you can take, and we will focus today on this path of the physics warrior. Okay, so of course the path of the mathematician would be worth a different talk, and Aaron Debray certainly would be a perfect candidate to do so. If you want more details, I'm also willing to give more information on that at the end of the talk. But today we'll focus on this piece of information that is more related to physics, breaking of symmetries, defects in string theory, and so on and so forth. Okay, so first of all, let's define what really the structural information that defines our Bordism group is. So we're interested in investigating type 2a, including the structure of the space-time manifold as well as the duality bundle. So the first answer for what is the duality bundle would be SL2R, that's the supergravity. But then you have flux quantization that already gives you, well, you should actually restrict this to integers, so it's SL2Z. However, that's also not the correct answer, because the fermions transform differently under duality than the bosons do in the low energy effective action. And similar to rotational action of SO that lifts to a non-trivial extension given by the spins bundle, the same happens for duality. So now you lift SL to some double cover, which is known as the metaplectic group. And as I told you, because now this distinguishes bosons and fermions, so fields that are classified by their space-time symmetries, and mixes them with their behavior under duality. Actually, the duality is not anymore a pure bundle information, which would be the case for the SL2Z, but mixes with a spin structure of the space-time manifold. This is known as twisted spin structures. One of the most famous examples would be a spin C structure, where we have the mixing of a U1 gauge bundle with a spin structure of the manifold. So in our case, this would be the spin MP2Z structure. This is also not the full answer, because there's orientation reversal that also acts as a symmetry. So instead, one could extend SL to Z to the general linear group, basically adding a 2x2 matrix with integer entries that has determinant -1. That's the one element that distinguishes these two things. And the full answer then would be actually a combination of the two. So now we're in GL, so that's not orientable anymore. But we still need a double cover that allows for the spinners to transform under that. And there's two ways to do that. It's a pin plus or a pin minus structure. And the correct answer for type 2B is actually a pin plus cover of GL2Z. So that's really the full duality group we want to discuss. And again, you see that there's this twisting between space-time geometry and duality information. So the corresponding Bordism group would be omega D of spin GL plus to Z. So this GL plus is just the pin plus cover of GL. Okay, so this already looks quite complicated, and indeed it is. So just to summarize, so we really are interested in these Bordism groups, and let's forget about the first one because it only sees about the bosonic action, and we really want to include the fermions because they're there in supergravity, right? So let's focus on the other ones. They're more complicated and to calculate anyway. So there we expect that this is the more accurate information, or we're sure that this is the more accurate information. Okay, so just as a reminder, if there is a boundary condition for all of these potential compactification manifolds classified here, then all of those omegas should be vanishing. Then we're happy because there's no global symmetries. So in order to see that, you would actually have to go to the left part of this map and really go through spectral sequence technique. So the main tool that we use is the atom spectral sequence. And there are some subtleties where basically we do a prime decomposition of the different parts. And there is so the duality group behaves nicely as some amalgamated product that helps a lot in the computation, basically into splitting into easier parts. Some can be found in the literature. And for all spectral sequences, you're actually not getting the full answer in the sense that the end will be the final group that you're interested in, but it will be a filtration and you still have to solve an extension problem. And we solved that so we solved this extension problem. And in many cases, we could basically calculate some topological invariants that were able to detect all the necessary classes. So by saying that, you already assume that probably there are some that are non-zero, and we have to work a little harder to make them zero. And indeed, if you look at the full group of Bordism groups, you see that there's very few that vanish. And there's a lot of non-vanishing entries, and all of those would be actually problematic for the Cobordism conjecture, or essentially for the no global symmetry conjecture. Okay, and also note that we actually calculated them up to dimension 11. So these first 9 dimensions are the ones that are interesting from the Cobordism conjecture perspective, but I will have a little bit to say about this dimension 10 and dimension 11 pieces. Okay, so this is the math in just 2 slides. I basically give you the result, and now let's try to interpret what is really going on. So in the first part, let's focus on the spin MP2Z. That's the city of Metaplektia in our map. You already can see that there's a torus here. So maybe there's a connection of type 2B and F theory, and that turns out precisely to be correct. So why is that so? Because, well, we just said that our manifolds needs a spin MP2C structure. And it turns out that this is actually equivalent to a spin structure and on a torus vibration. And we know that type 2b has a very nice non-perturbative realization by just lifting the axiodilaton to the complex structure of an auxiliary torus, and this is given in terms of the description of F theory. Okay, so now our picture, when we want this spin MP2Z manifolds to lift to like from type 2b to F theory backgrounds, we have our base of the F theory vibration that becomes the manifold that we need the boundary condition to. And then on top of that, we have the torus fiber that encodes the duality bundle and essentially this MP2Z transformations. And in usual F theory geometry, if you want to preserve some supersymmetry, you do it in such a way that this base and the fiber combine into some genus one fibered Calabi-House space. And then, of course, we have this non-compact piece of space-time to which we want to define the boundary condition. Okay, so let's look at the easiest example here. That's where the dimension of the base is one-dimensional. So that's this Bordism group, and it's given by Z24. And not by coincidence, this is also the abelianization of this duality MP2Z. So the abelianization, you can simply calculate what it is, and it turns out that it's C24. So how can I understand it? Well, the space-time manifold in one dimensions, there is not much choice for compact space-time manifolds. It's usually just a sum of disconnected or a disconnected sum of circles, and that turns out to be correct here as well. So the generator of this group, the one manifold that you cannot deform to nothing, is simply given by a circle. And if you go around the circle, you have to act with a duality transformation in this duality group MP2Z. So in a way, you can think about it either as twisted boundary conditions for your fields, twisted by the duality transformation, or equivalently, you could think about it as a background connection for a discrete gauge field that tells you that, well, there is this duality bundle around the circle. So now this is the type 2b picture. This is the manifold that we need to be able to deform to nothing in order to satisfy the Cobordism conjecture. Well, let's lift it to F theory. So let's put a torus on top, right? So now I go around the circle and my torus undergoes an MP2Z transformation. But in F theory, we have a very well understood picture of what it should be that sits sort of as a defect inside the circle that generates this monodromy transformation. It's in general just a stack of PQ7 branes, right? So you know precisely that if you have a PQ7 brane, then this induces an SL2Z, and more general, if you include the spin structure, an MP2Z monodromy around it. So basically the Cobordism conjecture, even though it doesn't know anything about 7 branes, tells us, well, there is a class that you cannot deform to nothing unless you include a defect that awfully looks like a PQ7 brane, and that's what it is. And again, we have this picture before that the defect that you have to include sort of has some singularity in terms of the structure defined. And for this torus vibration, this means that the torus pinches. And once you include this PQ7 brane defects, then you can describe the circle as the boundary of a disk where there is this PQ7 brane generating the monodromy. Okay, and of course you see that by this abelianization, you lose a lot of information about this PQ7 branes because they have non-trivial braiding statistics and they're much more diverse than just this Z24. And indeed, going a little bit away from this pure topological information in the Bordism conjecture, we had something to say in like moduli spaces of genus one vibrations in this paper with Jonathan of 2020. Okay, so this was the simplest case, and what we found, without any input but the structure of the duality group, you have to include PQ7 branes in order to satisfy the Cobordism conjecture. So let's go to another example. Let's do it. Yes?
I have a question. So
sure.
The previous picture, so this is just you have a non-trivial elliptic vibration over a disk, which is a two-dimensional base space. So we are dealing with an 8-dimensional F-theory model. which is a dimensional supergravity, or so because in the picture on the left, that was like a 9-dimensional supergravity.
That's right. So what you should think about is more like take this picture, right? And on this side, just extend the circle to become a semi-infinite cylinder to one side. And then what this looks like is a 9-dimensional supergravity that ends. And this is precisely the boundary condition that I was talking about. So it's a 9-dimensional supergravity that comes from a compactification on this circle with monodromy that has a well-defined boundary condition once I include the PQ7 branes, and they can stop there. Of course, then you can do the mapping to a disk where in the middle you have the PQ7 brane.
Okay, so you have a, I see, so you have a, so the F3 picture is like the 9-dimensional system coupled to a 8-dimensional.
Yes, precisely.
Thanks. And all of both of the systems are coupled to gravity, right? So these are
so the gravity lives the gravity is an essential part here.
Okay, thanks.
Sorry?
Thanks. Yeah.
Okay, you're welcome. Great. Yeah, please feel free to ask questions anytime. So let's go to the next example where the base is 3-dimensional. Again, the Bordism group will not be trivial. It will be a little bit smaller. It's just a Z2 and a Z3 factor. And once more, we can ask what are the generators? And it turns out the generators, now from the type 2B perspective, are given by 3-dimensional length spaces. So those are the quotients of spheres by a Zn rotational group. Once more, this is not everything. So this would be the geometry, but on top of that, you have the duality bond. So what happens is this length space has a non-trivial torsion 1 cycle. And if I go around it, there is again a duality transformation. So if I go around it, my F-theory fiber undergoes a monodromy. And that is the configuration that generates actually both of these factors here. And for a mathematical interpretation of this, you can, for example, use something describing the 3-dimensional sphere as a Hopf vibration of S1 over P1, and then you take a Zn quotient. However, again, we know this configuration, and we know that it arises as asymptotic boundary of something that looks like a complex line bundle O minus n over P1. So that is essentially closing. So if you have the S1 as the fiber in the Hopf vibration I told you about, you can close it into a disk, and then it will be a disk bundle that sits inside this complex fiber bundle. And this configuration is well known, again, from F-theory perspective, because it's describing a so-called non-Higgsable clusters. Okay, so these non-Higgsable clusters would be a resolution of a singular geometry that you can just think about as a torus fiber times a 2-dimensional complex plane modded out by a Zn action. Okay, or in other words, there is it's a non-compact configuration where you have a curve of self-intersection minus n sitting in the middle. Question from Craig?
Yes, I see you noticed me. Thank you. I'm a little confused about this. So this is really a compactification of F-theory to 7 dimensions on the lens. So the cobordism is a space which extends this lens space to a point, as you were saying, but you're not studying F-theory on the cobordism itself, which so I'm not sure what the connection to the non-Higgsable clusters are with the cobordism space.
So we have a generator that with a structure that is defined, or the structure that is the input information cannot be deformed to nothing. And then we ask ourselves, can we find this space as some sort of boundary in an F-theory configuration? Okay, and this means F-theory now living on the D+1 dimensional space that has this D-dimensional space as a boundary. And that's precisely what's happening here. So we basically extend it in a radial direction, and what sits in the middle is a collapsed non-Higgsable cluster where I collapse the collapsible curve, the -n curve.
Okay, I see. So maybe if I can just make sure I understand this point. So the 7-dimensional thing is not contractible to a point. It's not cobordant to a point. And the point is, it's not cobordant in some kind of smooth way consistent with the
Precisely,
and so on. But
correct.
if you allow yourself to talk about things which go cobordant in such a way that something becomes singular, then you find that you can make it cobordant to a point. And
that's correct.
Every time
and
you
then,
sorry, go ahead.
And then the question is, well, can we find a good physical interpretation of what this singularity is? And in the cases that, in the MP2 cases, we actually find a lot that are just F-theory backgrounds that we know and love. So we perfectly know what the corresponding defects should be.
Yes. And you say that shouldn't be surprising because you're taking basically an elliptically fibered space with some singularities. And of course, people think about F-theory on these things.
Well, it could still have gone wrong in the sense that we could still have found backgrounds that are not possible to interpret in F-theory terms. And we'll come to that when we go to spin GL+, which of course then there's something more involved, more structure than you would see in F-theory. And yeah, this will lead to new stuff. Okay, cool. Thank you. So again, we basically started without any information about the 60. So these non-Higgsable clusters, by the way, are very important because they're form like a very simple parts and building blocks of 60 superconformal field theories. So again, without any more input information, we found very non-trivial F-theory backgrounds that appear in this study for 60 SCFTs, for example. So let's go one step further. Let's take the dimension of the base to be 5. Bordism group, again, non-trivial, and it becomes large again. So we have to account for several factors here. Once more, the type 2b background would be described by a 5-dimensional length space, where again, if I traverse the torsion one cycle, I have to put a duality transformation that acts on the fiber, right? That has a singular representation in terms of this T2, which is the F-theory fiber, times a 3-dimensional complex space modded out by a Zn action. So basically, the Zn action on T2 classifies the monodromy action. And once more, these backgrounds are not new and well known and highly non-trivial because those things, so the defect that would sit in the middle here, are described by so-called S-folds. And those S-folds are famously those objects that lead to n=3 supersymmetry in 4 dimensions. So again, without any more input, we find that our Bordism basically tells us you should look at precisely those backgrounds that then lead to highly non-trivial interpretation in terms of quantum field theory or F-theory background. And then we can push it further. Oh no, there is one thing I want to mention. So in fact, so there is this 2 in prime 2 order, these 2 parts, the Z2 and the Z32. And they're actually related to the fact that when I have a length space given by S5 mod Z4, by the way, this space does not allow for a spin structure, but it has a spin Z8 structure. And funnily, it has not a single spin Z8 structure, but it has 2 different ones. Okay. And those 2 different spin Z8 structures will be precisely those 2 factors in the Bordism group. And if you study how the supercharges behave, then you will find n=3 S-fold, but you will also find n=1 S-fold. So there's like a new type of S-fold that does not preserve all the supersymmetries, and so it only preserves n=1 and is associated to the choice of spin Z8 structure. And this is essentially something that was studied also from an M-theory perspective. They would start with a space like S7 mod C4 that is a spin manifold, however, has more than one spin structure. And this is the F-theory lift of this configuration. And basically in this paper that will appear somewhat later this year, we discuss, well, how are the central charges in these two different theories related? Because they're very, very similar. They're just this topological choice of spin Z8 structure that distinguishes them. So can we sort of save some of this very restrictive part of the n equals 3 also in this n equals 1 analog? Okay, so now
I have another
yes.
question. So
Sure,
for
of
these
course.
interesting cyclic groups like Z32 or Z9 on the previous slide, so what are the F-theory physical interpretation of these groups, Z9 and Z32?
So this is just so essentially what it is, it's a refinement of the order of the element that you mod into here. So basically you can think about it as, so how many of those S-folds do I have to stack on top of each other such that they combine into some trivial monodromy structure in a sense? That it's C9 and not C3, which would come essentially from the MP to Z, is associated to the fact that you have more topological information. So a good way to think about it is if you encode the duality bundle into some discrete gauge field, going up in dimension tells you that there are more cohomology classes associated to that discrete gauge bundle. Right? So you start out with a Z3 connection, but then you can combine it, for example, with parts from space-time geometry, like a Stiefel-Whitney class. And this going up in dimension usually makes the number in the Bordism group go higher because you have more non-trivial backgrounds in these setups.
Oh, okay, and that's something universal, that's also independent of the little n. So
that is relatively universal, but there are some caveats because sometimes it collapses, and I will come to again a situation where it collapses in the spin GL plus part.
Okay, thanks.
Okay, so we can push that further in dimension. The backgrounds are very similar, so we always get this T2, the F-theory fiber times the base C4, C5, and so on, that we can map, and we find new S-fold type geometries. So we call it, according to the dimension of the defect, could be interpreted as some S strings, some S instantons, and you can analyze the supersymmetry. That can be very exotic, but again, to have a full answer what the supersymmetry is, we would need to know what the induced Rameau charges are, because they have an influence. So induced Rameau charges tell you essentially you have to put on top of this background. So as for the S-fold, by the way, you have to put on top of that some D branes or some strings or something. Okay, and we're not sensitive to this information in the Bordism by study. Okay, so that is
the N is 2, 3, 4, and 6, or can it be other things, other values? So
if you want to have a good action on the torus, it's precisely what you said. It's 2, 3, 4, and 6.
Okay, good.
Yeah.
Okay, thank you.
So it can, so at least the n that acts on the torus can be 2, 3, 4, and 6. But of course, it might be that it's larger, but only the square of it acts on the torus. Then it can be Z12, for example. But, yeah.
Okay, I see. Thanks.
One class that appears that is a little bit different is sometimes actually the base space is itself a vibration. So there is one generator in dimension 7 that is not of S-fold type, but it's more like a lens space, 5-dimensional lens space fibered over a P1. And this 5-dimensional lens space appeared in the lower dimensional Bordism groups. So we know that we can basically put an S-fold inside here, and then we can close the fiber, and this also bounds this whole vibration space. So we basically have the S-fold theory compactified on a P1, but compactified with a twist, because the vibration structure here is non-trivial. So again, without further information, the Bordism calculation points us in a direction saying like, you should include also theories with topological twists, okay? And this concludes my discussion of this F-theory backgrounds. All of them have some realization as a supersymmetric defect. Also, these topological twisted theories will be preserved part of supersymmetry. Again, at least with a caveat that we have to add Raman-Raman fields potentially. And so this is my summary here. So all defects preserve part supersymmetry and have a nice F-theory interpretation. In the spin MP2Z case, which might not be too surprising once you realize, as Craig said, that, well, spin MP2Z structure is a spin structure on a torus vibration. So that's what F-theory is about. But still, it's quite astonishing, or it was quite astonishing for us, that this bordism calculation really points to various highly non-trivial F-theory backgrounds with very interesting dynamics. And now with this part, let me actually move to the next level where we add reflections. So we go from spin MP2 to spin GL+. So we include now the element with determinant -1 and its associated spin lift, or pin plus lift, I should say. And this is related to this fortress of the queen of reflections in the map. Okay, so what should I expect? There's two answers. So I start with spin MP2, and now I add elements. I weaken the structure. So should I expect more? Yes, there should. Well, every spin MP2 manifold, right, is also a spin GL+ manifold. So there should be now more bordism generators. But I should also expect less, because now the deformation classes, something that was singular in spin MP2, might be fine in spin GL+. So I allow more deformation, so I allow more identification between the different bordism classes. Turns out that both is correct, and the answer whether you find more classes that are non-trivial or less depends on the dimension. And this is precisely what I wanted to tell when Yinan asked the question whether, well, is it a general rule that things become larger if I go up in dimensions for the bordism group? I would say yes, but there are some caveats on the way, and this would be one of them. So let's take an example how this happens, again, in the simplest context, namely where the base is one-dimensional. So now you see that the group before was Z24, that's Z3 plus Z8, and now it's only Z2 plus Z2, so it became smaller. Now one of the Z2s actually is a leftover of the spin MP2 manifold, so we know about this. This again will be cured by PQ7 brane. However, the other factor, Z2, is not. Okay. And so this involves a new object that was studied in the paper with Ethan, Miguel, and Jonathan. And basically what this tells you is that there is one more bordism generator that you go around the circle, and you have to do one of those monodromy that involves a reflection. So now you have to include a 7 brane that has a monodromy that has a monodromy matrix, which is determinant -1, and we called it, for obvious reason, a reflection 7 brane, or R7 brane. And those would be good boundary conditions for well-known 9-dimensional string backgrounds. So there are two variations. So you can take the worldsheet orientation reversal given by omega when you go around the circle, then this would be known as Dabolka-Park background. You could also take the left-moving fermion number as a monodromy if you go around the circle, then those are known as the asymmetric orbifold background. Okay, and those two are S-dual, so they are both generating the same element in here. Now let's see if we can understand that actually we find less than in the spin MP2 case. So in the spin MP2Z case, we found a Z3 factor, and let's say this is given precisely by a generator. So this is a Z3 generator here. Okay, so Z3 means I take 3 copies and I can deform it to nothing. So I take 3 copies, and this is essentially the monodromy. So it's basically a partition function, or this classifies a flat background field, if you want, whatever your favorite perspective is. It just tells you that you can define it to nothing, meaning if 3 transition functions with the arrow in the same direction meet at a point, they go to nothing. Okay, but what you can also see is, like, there is no way you can start gluing this boundary to this boundary here, because the arrows point in 2 different directions, meaning that that you have no consistent gluing here. Now, what happens if I include reflections? Well, reflection acts on this element G here and turns it into its inverse. So what I can do is I can include a monodromy of this reflection brane, R here, and that actually flips the arrow. So G goes to G to the -1. And what you can see is once I include now reflection, and this is not, sorry, I shouldn't say this is associated to a reflection brane, it's a flat duality bundle that has a transition function or implies a transition function that contains reflections. This allows you to flip arrows here. And now you see so this was the spin MP2Z structure. In spin GL plus structure, I can just include that as a flat background field and I can flip arrows. But once I flip the arrows, I can now glue this boundary onto this boundary here, and I end up with a two-dimensional manifold that has this circle with a transition function G as a boundary. And that's precisely the configuration that tells you that the circle with G is actually trivial to, in spin GL plus Bordism. So we started with something that was non-trivial. We included reflections that allowed us to, well, generalize the deformation classes. And in the end, we find that the element becomes trivial. So that is true for 1 dimensions. We go from more to less. It turns out that in dimension 3 mod 4M, so 3 mod 4, 3, 7, and so on, this is not the case. And the reason essentially is that, as I said before, often you can associate these non-trivial Bordism classes to some sort of topological information encoded in the duality bundle. And if the duality bundle, if this cohomology class of the duality bundle flips sign under reflections, then you can do this gluing of parts and you find less. But for example, if it's quadratic in this gauge field describing G, then you just get twice a -1, which is +1, and the gluing doesn't happen. Okay, so in dimension k equals 1 plus 4m, you find less in spin GL plus, and in dimension 3 plus 4m, you generically find more. Now, what are the objects? What are the things that we have to include in lower dimensions? Well, it turns out that, again, even in the spin GL plus, some of the backgrounds we find can have a supersymmetric interpretation. Namely, there is one background that is essentially a 3-dimensional real projective space where over the non-trivial 1 cycle, we now have an omega monodromy. And this can be thought of as the boundary of an O5 plane. Of course, you can also take into account the S dual of it, then it would be a -1 FL monodromy, or the left moving fermion number. Again, the same caveat, we're sensitive to the duality structure as well as the space-time geometry, that all fits. However, we don't know whether this object should have the correct Raman charge a O5 plane does. Okay. And the other operator is very similar, but instead of omega, you do a combination of omega and one of those standard SL to Z transformation, which in this case would be at the S generator. And once more, we can have a sort of understanding of what is the field theory, sorry, what is the string theory object that satisfies that. Well, we had the R7 brane that generates the omega monodromy, right? So now we essentially take the same trick we did for the non-Higgsable clusters. We take a curve of self-intersection -2, we wrap a combination of reflection and PQ7 branes around it and then collapse it. And so this is given by a space-time like that, and we'll have an asymptotic boundary precisely of that form. So there's, again, very interesting backgrounds to be discussed here. And the important information is that you actually don't have to include more objects than the R7 brane to get rid of all the Bordism classes also here. But with that, let me, there's also, of course, if you go up in dimensions, there's more diverse things. You have non-trivial vibrations as before, often spin MP2 survives. But I don't want to go into much more detail here and really focus on this interesting new 7 brane, namely the reflection 7 brane that was studied in the paper last year. So first of all, you can ask the question, well, what happens with supersymmetry? So you take this R7 brane, you know the monodromy, you know the action on the supercharges. So you can essentially study what happens if I take a supercharge and carry it around the R7 brane. You'll find there is no covariantly constant spinner, so supersymmetry is broken. Of course, this is now a problem because, well, now all the computational tools become a bit harder to access. So all the information we get should be topological information, and should be taken with a grain of salt that it's very hard to verify it in a nice dynamical system. However, now what is very different for the R7 brane compared to any PQ brane is that it also have a non-trivial action on D3 branes. And the reason is that this omega acts also on C4, the four-form Raman-Raman field, which tells you that you can take a D3 brane, you can carry it around R7, and it ends up being an anti-D3 brane. So this behavior of taking a charged object, carry it around some string-like configuration, it ends up as its own antiparticle, is known as an Alice string. So in a sense, the R7 brane acts like an Alice string for D3 branes. And there is funny things you can do, like charge teleportation and the like. Now, even without the R7 brane, you might ask the question, well, can we generalize the concept of F-theory to include now monodromies, not necessarily involving the branes generating them, but for example, if we consider general compactification manifolds that have a non-trivial H1, so those would not be Calabi-Yau, but you could think about it. Now, there's another hint that supersymmetry is generally broken, but it's harder to see, is that now you have this anti-holomorphic involution, because, well, the reflection really flips one of the coordinates on the torus, either it's a reflection on the diagonal or along one of the sides. And, well, this flips tau into plus minus tau bar, depending on what you take. But, well, maybe these backgrounds are interesting and can be generalized in a F-theoretic sense, and we have something to say about those in this paper. And, well, I'd like to call them like reverse F or Fe or whatever you want to call this symbol. It's like the flipped F-theory model. And maybe there is some perspective that you can use that. Okay. So now you can ask, like, well, we know that on D branes or PQ7 branes, there will be some strings that end in general. And now there is a sort of a lassoing technique that we also used in other work with Hao Shang, Ling Lin, and Miriam Cvetic, where we analyze, like, in a pure F-theory models, what string do and how they can end and what this implies for the global realization of gauge groups and so on. But here you can do a very similar technique for the R7 brane. So the technique is as follows. You basically take a string loop of general string charge SR. Now under the monodromy going around the R7 brane, this will flip it, for example, to S minus R. And you can just carry out the leftover charge into an infinite, semi-infinite string that goes to infinity, right? And then you can collapse the string loop on top of your defect. And this basically tells you that at least an even number of strings, and it's a bit more subtle to argue that also a single fundamental or D1 can end. But this suggests that F1 strings should be able to end on the omega reflection brane, whereas D1 strings should be able to end at least in pairs on this -1 to the FL brane. But of course, this tells you that, well, at least the world volume theory should not be completely trivial, because now you're letting a string end. So there should be something on the brane that absorbs this string charge, right? So on the D brane, for example, you find a gauge field that is able to absorb your string charge. So there has to be something that lives on the brane. But I told you that the R7 brane is special in that you can do the same thing with D3 instead of strings. So let's take the same configuration. Let's loop around one of the directions of the D3 brane, then collapse the circle. And this tells you actually that a D3 brane should be able to end on our R7. And that's now very different from the 7 branes in F theory because, well, C4 is trivial under MP2C. And once more, there should be something that absorbs the D3 brane charge. Right. So if you want the picture, so this is now really the world volume of the R7 brane, and you have a D3 brane that ends in one-dimensional lower subspace, so a three-dimensional submanifold of your R7. And this should imply some transverse flux in this 8-dimensional world volume. So the transverse sphere would be 4-dimensional. So this suggests that there should be some flux that you can integrate over a 4-dimensional sphere, and the natural object where this is possible is a 4-form flux. So the flux of a 3-form field. And those 3-form would necessarily be localized on our R7 brane and will behave odd under reflections because the D3 brane does as well. So this suggests that there is a massless 3-form field living on the R7 brane. And then, of course, we would like to make very strong conjectures. And now we have a massless 3-form that behaves very funnily under S duality, right? So maybe it's a self-dual complex 3-form field. And if you have self-duality, then this points towards a strong interaction, or at least the interaction of the 3-form. So if we could have made this more precise, which unfortunately we were not able to push it to really a conclusive argument, then this would be a hint of actually a non-supersymmetric interacting conformal field theory in 8 dimensions, which of course would be very exciting in its own right. Okay, so I don't have much time, so maybe let me just say couple of words about these other bordism classes that I haven't mentioned so far. So for k equals 10.
Can I ask a quick question about the R7?
Yeah, sure.
So is there something like a PQ R7 or?
So yeah, there is. So I would say there is these 2 versions. There are S dual, which, however, from Bordism perspective, yeah, from Bordism perspective, they're the same thing. So you don't need to include both, but they come naturally as boundaries of these 2 type of 9D string theory backgrounds.
So there's 2. Okay, thank you.
But they're connected with moves. So basically, what you can do is you can connect them by taking R7 of one type, then generating a PQ7 brane that has a S monodromy and its inverse, and then carry it around and re-annihilate. And then this process that doesn't involve any more R7 brane will turn the one R7 into the other type. So that's saying it's an S dual. They're the S dual versions essentially.
Okay, thank you.
Okay, so in dimension 10, those things are also interesting. They classify topological actions related to theta angles, which we don't really know whether they should be there or not. And it's an interesting debate. And in dimension 11, those things are related to actually anomalies in the duality symmetry that has been analyzed in this earlier paper by Aaron, Jonathan, Miguel, and myself, and has some interesting implications. Let me just come to the conclusion here. So I hope that today I was able to show that the investigation of bordism groups can have, in general, very surprising results, and that the input information is rather trivial or very, very limited, but still it points in very interesting direction, namely finding or rediscovering various objects like 7 branes, non-Higgsable clusters, S-folds, pointing to new objects, and of course having also an impact on topological terms, anomalies, and so on. And this is both a test and predictions of the Cobordism conjecture as a generalization to this no global symmetry conjecture. And just as an outlook, I think this is just in some sense a beginning. One I already told you about is this new type of S-folds that are related by different choice of spin Z8 structure that we're studying at the moment. and there is this reverse F theory models. And of course, what would be very interesting to apply these things to other type of dualities, like T-duality, R symmetries, and revisit those dualities, for example. And another thing that would be very interesting, and we're just at the beginning to explore, is take all those defects that you needed to include in type 2b and basically trace them through the whole duality web and see what becomes of them in type 2a, M theory, heterotic, and so on and so forth. Okay, and with that, thank you very much, and I'm open for your questions.
All right, let's thank Markus. Questions?
I have a question. So is it possible to think of the R7 as sort of an O7 plane, but without the parity reflection? Is this the correct?
That's right, yes. So the O7 plane in type 2b would have both the omega and the -1 to the FL somehow. And sort of we separate them into parts. You can even do that more, and we have more on the paper in the sense that you can start with an SO8 background that has on top of the O7 also a couple of D7 branes. And then you can deform this, you can basically pull this to form the -1 to the FL in the omega brane. And this is also like a decay channel. If you reverse the pulling away, then they will collapse and form the supersymmetric background plus radiation, for example. So yeah, there is a connection, but they're different in the sense that they're more related to building blocks rather than the clean orientifold interpretation.
Okay, thanks.
So you very briefly showed a very interesting drawing on the page before.
Mm-hmm.
I would like to see it.
Yeah. So,
can you say a few words about this?
Sure. Yeah. So the point is, so there is on one hand side there is this topological terms that in principle could be so those are topological actions in 10 dimensions that depend on the duality bundle and spacetime. And in principle, if you have such classes, you can add terms of the discrete theta angle terms in your action. Right? So this is discrete information that just tells you in the full partition function, you would weigh a background that has these topological features with a -1 and other backgrounds that don't have these topological features with a +1. In principle, you can include that. That is a well-defined 10D action, at least from the viewpoint we have today. But then you have two values, right? You have theta equals to 0 and pi that is allowed. So one doesn't do the different weighting, the other one does. So in the end, you get different 10D actions. And this is also related to, there is an anomaly for this duality that you can cure by adding some terms in the action, which that we discussed in that paper. And that would also come in possibly different varieties. And then if this is true, it looks like the duality star, where we have a single type 2b theory, a single type 2a, would split into more like a duality flower, where the different petals of the flower are related by different choices of the topological sector of the theory. And in principle, at the moment, we have no real guideline is whether is it allowed to have these different topological sectors, right? So then you have this, then they should be connected somehow, and there should be domain walls, which would be very interesting. On the other hand, maybe they're just forbidden, and then there would be some sort of new consistency constraint, or if you want to phrase it as a Swampland constraint on this 10D supergravity effective actions. Yeah, and that's what this figure is about.
Okay, very nice. More questions?
Hi, Markus. So for this
Hello.
duality flower, are the number of branches like exact statement or just
No, it is very random. depiction of you know, how much time we wanted to put in making this figure, because it well no, you shouldn't view it. I mean, you definitely in type 2b, I gave you a partial answer, right? Because I told you the spin GL plus at least has 4 of those discrete theta angles. If all of them are okay, in principle, there should be 4 different versions, or actually 2 to the 4 different versions, all of them theta equals to 0 or pi. Okay, so they're already quite a bit more than I drew in this figure here. And then the fact that also the other split is essentially in most of the situations is conjecture. Why not should type 2a have something like that? There is some discussion in M theory. There might be a M theory theta angle that has been analyzed, I think, by Fried and Hopkins in a paper where they also have some Bordism calculation of a so-called spin MC structure that is a bit different than what we had for type 2b. But yeah, this is the number of dots here. This is just, you know, it's a cartoon of what might or might not be true.
Okay, yeah. Thanks a lot.
Can I ask just a quick question? So is there some way of getting some kind of classification kind of statements out of this? So you said you could generate S folds from looking at, you know, how to make things cobordant, etc. So do you get all S folds? I can also ask this question about non-Higgsable clusters. Maybe that's even easier.
You can also ask the question about PQ7 brains.
Indeed.
And there the answer actually D7 is enough. So it turns out that the D7 brain is a generator of the Z24. So purely from this Bordism viewpoint, which has only very coarse information that you can access, D7 would be fine. But then when you go down in dimension, right, you find the non-Higgsable clusters, for example. And there we need already something that generates more than just the SU gauge group, because we find the -4 and the -3 cluster. So we have an E6 or we have a SU3 strongly coupled and a SO8. And for those, you need already a couple more PQ7 brains in this interpretation. But yeah, it's very hard to state that you find always everything. I would not know a good argument for that. In our case, it seems to be a rather complete list and pointing towards interesting backgrounds, but yeah, I don't know. Also, you can do the combination. So there's in principle an S fold that is a Z6 quotient, and that is enough to break both of these groups, because the Z6 precisely has the Z2 part and the Z3 part. And there's always these choices. We chose like the minimal set, or I should say the easiest generators and the associated objects. Yeah.
I see. Cool. Thank you.
Any more questions? Well, if not, then let's thank Markus again. And I'll stop the recording.
Thank you very much.